Hello everyone and welcome to yet another math video. In this video I'm going to be going over how to transform the graphs of parent functions. And in this first example, actually first two examples, you'll see that there is no parent function given here, no particular equation like quadratic or square root or so on. Instead, we are just given a function f of x on the right as the parent graph. So this is just the parent graph, some random piecewise graph. But we can still transform it. So you can see here, describe how a point on the parent graph is transformed using translations and or reflections, then draw the graph of the function. I'm going to expand on this a little bit because if you don't know what the points of the parent graph are, then you can't tell me where they end up. So in order to graph these, first I need to create a list of parent points like this. And so maybe one more right here. I want to pick the points that make sense, going back to thinking about whether a function is increasing or decreasing or constant. Starting from left to right, it's decreasing. Oh, it changed. Okay, so that's probably an important point to have. And right here at this point, it changed from increasing to constant. Probably an important point to have. And I used one more point so I know where that arrow is supposed to go. And that's my thought process there. So what are these 4 points? They are listed out here in this table. So what goes on? In order to figure out where this graph is moving, we need to look at what is given to us. So here we have y equals f of x plus 1. Oh, that plus 1 is inside parentheses with x, so it's going to affect the x values. And outside we have this minus 2. So that means this will shift left 1 and down 2. How do we make that appear in this table over here? Well, you take what's inside the parentheses, in this case x plus 1, and we're creating many little equations here. So x plus 1, and then we can solve each of these little equations by, well, solving it. We can recognize that all of these are going to be solved by subtracting 1 from the current x values because all of these equations are exactly the same. So they will be solved exactly the same. So we can come through and start out new x's, and we just subtract 1 from all of these old x values. So we end up with -5, -2, 1, and 3. Now with the y values, this is happening outside, so it happens to the y values, right? It's not grouped up with x. But additionally, it will do exactly what it's telling you to. So that -2 will take 2 away from all of these y values. So that'll leave us with 2, -4, -1, and -1. And those are the new y values. So what we do is we plot all of these new points on the graph. So here, hold on a second, there we go. So I will plot a -5, comma, positive 2. So that's, -5, positive 2, that's that point right there. -2, -4, which is that point right there. 1, -1, which is that point right there. And then 3, -1, which is that point right there. And since I went left to right as I wrote these down like this, I can connect these left to right, and you'll see that the shape is preserved exactly as the shape that's over here. All it did was move left 1 and down 2, and left 1 and down 2, and left 1 and down 2, and left 1 and down 2. And we get this exact graph. I will do part B on the next slide. Part B will go a lot quicker because I've already set up a lot of this in the last example. So that being said, over here in the part B function equation, I can see that there's nothing going on with the x, but what the +3 will do is it will move the graph upward 3, and this negative here will reflect over the x-axis, aka a vertical reflection. And we know it will be a vertical reflection because this is not grouped up with x. So in order to do this correctly, you must multiply, aka do your reflections first before you do any shifting. So I will multiply all of these by -1 to get new y values, -4, +2, -1, and -1. Then you can go through and add the 3, which will give you a -1, a 5, a 2, and a 2. Now again, I'm going to plot these x's with the new y values over here. So that gives me a graph for -4, -1. Then -1, 5, then 2, 2, and 4, 2. So that'll be 2, 2, and 4, 2. And again, since I wrote these points from the original parent function left to right, you will connect these dots left to right. So I will do this, I will do this, and then I will do this with an arrow there as well. And you can see that the vertical reflection happened. This point went from above to below and then got shifted up 3. This point went from below to above and then got shifted up 3, above to below and got shifted up 3. Same thing with this point here. And we have the transformed parent function. On this slide and the next two, I'm going to go over how to graph parent functions of actually named functions within mathematics. Like part A will be on this slide, that is representing a quadratic function. Part B on the next slide will be an absolute value function. Part C on the third slide will be the square root function here. All right, it's going to be very similar to the last two examples in that we need to know the parent table first. So we've got to find the parent table, and in order to do that, I'm just going to say, hey, for part A, let's list out the parent function, with the square being the defining feature for this one. That's what it's going to be. It's going to be x squared. Now, how are you supposed to find the parent table? Well, it will always be x and y. And for the majority of parent functions you will look at, you will want to pick these values, -2, -1, 0, 1, 2. And then to find the y values that go with this, you can just substitute the x values in for x and get the y values in return. So 4, 1, 0, 1, 4. From here, we just go through and apply all of those same ideas from the previous couple examples. We have f of x equaling -x plus 4 squared plus 9. And what this means is that since this +4 is grouped up with x, it will move the graph horizontally. In fact, it's going to move it in an opposite manner. So this will go left 4. The +9 out back will move the graph vertically, but in a normal direction. So if you add normally, that makes things bigger or shifting up. And then lastly, with this negative, this is a vertical reflection. There we go. And we're just going to use the same principles. It's just that this time around, we didn't know what the table was to start with. We didn't even have a graph to get the table from. So you have to create that table on your own. But very similarly, we can take what's inside grouped up with x, everything, x plus 4 equaling positive 2. And from there, once you figure out how to solve one equation by subtracting 4, we will just subtract 4 from all of those x values. So right here, I'll do the new x's. And if we subtract 4 from everything, it'll be -6, -5, -4, -3, -2. Now for the y values, just like in the very last example, we have to apply the reflection first, so multiply by -1. That's going to give you a lot of new values, like so. And then you're going to come back and do your addition. Remember, you need to multiply before you add, and you'll get some new values like so. And those are the new y values, so all we have to do is plot these ordered pairs, and we have ourselves a graph. So let's come over here to the right and graph this thing. So that would be -6, 5, -6, 1, 2, 3, 4, 5, right there. -5, 8, 1, 2, 3, -4, 9, -3, 8, and -2, 5. So here's where the points are, and then just make sure you make your graph. Quadratics are U-shaped, and just for reference, I've added some x's here that you can see. This is where the parent function sits. I'm not actually going to draw it, but I'm just putting them there for reference so you can see there's this U-shaped being created by these x's. And a reflection vertically means instead of being U-shaped, it's going to be upside down U-shaped, so that makes sense. And then it shifted 4 to the left and 9 up. So yeah, this blue graph is where it finally sits. So we have the transformations listed out here. We've got the parent function and table. That's the parent function and table here. We've got the transformed table over here. Oh, domain and range for the transformed function. Let's not forget that. That's important. So the domain, you can tell by the function here, there are no x's in a square root or in a denominator, so this will be all real numbers. That's the easy one. The range you can get from the equation, but I'd rather look at the graph. The range goes negative to positive in the y direction or bottom up. And since these arrows are pointing down, that means the range will start at -infinity. But where does the graph stop at the top end? Right here, that looks like a y value of 9. So there is the domain and range for this. All right, a little more setup this time around with the parent function and table already being provided. Remember, these are the x values you want to use for most parent functions. We'll see in part C how that changes. But then remember, you can get the y values by identifying the parent function first. Since this is an absolute value function, it's just y equals absolute value of x, and substituting the x values in here to figure out what the corresponding y values should be. Now, very similarly to the last example, we can just come along here and subtract 5 from all of these, and we can get some new y values. And we can also set what's inside here with x minus 2 equaling 2 to figure out what we need to do to these x values. So we're just going to add 2 to all these x values, and those are going to give us the new x's and y's that look like this. So a lot has appeared here. I went through and added 2 to all the x values, as I said, and then I subtracted 5 from all of the y values like it's telling us to do. And then I plotted these new x's and y's here. Meanwhile, I also plotted the parent x's here. I'm not actually going to draw that graph in just like the last one. So here is what this transformed absolute value function looks like. And for clarity, this will be a V-shaped graph. It has a very sharp corner here. It turns at a corner. So lastly, we just need to find the domain and range. And again, the domain here will be negative infinity to infinity because there are no x's in a square root or denominator. And then finally, the range, again, goes from bottom up, negative to positive in the y direction. So this time it bottoms out at -5. So I'll put a square bracket -5. And then it goes up forever to infinity. Let's take a look at part C. For part C here, we're graphing the square root of -x minus 4. And I've already gone through and found what these are doing, and I'm going to set up these equations so that this is -x equals 9, which means we will be dividing each of these by -1. So we'll have new x values, and we will also have new y values. The y values will only be having 4 subtracted from them. So as I create this new table, -4, -3, -2, -1, and the x's will be 0, -1, -4, -9. I want to go back and point out that the x values here changed for this one because, one, we can't, with the parent function, we can't have negative numbers inside a square root. So we can't start at -2, -1, but we can start at 0. And you notice I don't have 2 or 3 or 5, 6, 7, or 8 in this table because those x values do not give you whole number y value coordinates. So you have to be a little bit more strategic with square roots, and if you also graph cube roots, then you'll have to be a little more strategic in the numbers you pick for cube roots as well. That being said, we have these new x's and y's, so I'm going to go ahead and plot that over here. 0, -4, -1, -3, -4, -2, and -9, -1. And again, over here, you can see I put the parent x values like this, and here are the transformed points. So feel free to graph this in the way that makes the most sense there. I had to turn my iPad to graph that decently well, and even then it's not that great. So just do the best you can with graphing these. And now we can talk about the domain and range. So let's find the domain, let's find the range. The domain, again, negative to positive in the x direction. So left, oh, there's an arrow pointing left. So this time it'll be negative infinity, but the graph definitely stops somewhere. And that is right here. The x value here is 0, and we will include it. Now the range, on the other hand, starts in the negative y direction and goes up forever. So the negative y here is, or the lowest y here is -4, and we include it. And it goes up forever as the graph travels to the left. So it'll go all the way off to infinity. And that's it for this video. I hope you find it helpful. See you in the next one.